Okay, Tenav, let's rejoin for class. Adrian just posted a reminder in the chat of the schedule. It's going to zip by really quickly. This week we network, interface, wildcard, then these are beyond the lab, and then you're developing and presenting. So these are the cutoffs for the sequence to get as many of you through in this cycle. And I keep repeating over and over, work to the schedule, not the task. Make a calendar between now and finishing of what you have to do when. So today we're going to network. The individual assignment is design, build, connect either wired or wireless nodes and make a network. So until now, we've had single processors. Now you're going to have multiple processors. And the group assignment is connect two of your projects to each other, send a message between two projects. The featured project for this week is a really fun one. This was during the pandemic in Japan for machine building. What they did was made a musical instrument that was scattered all over Japan. So each of these instruments was in a different part of Japan, but they were all connected to each other. So why network? The obvious reason is location. I'm in Cambridge and you might be in Japan or India. So you need a network to send a message. But there are many other reasons. So a second reason to network is parallelism. As your projects get more complex, there are multiple subsystems and multiple functions. And so you need to do many things at the same time. One way to do that is go to a bigger processor, run an operating system, and have multiple threads. But the other way to do it is to have separate processors for each task. So we saw the magnetic imaging, and you might have one processor controlling a group of magnetometers and then another processor controlling the display. Or we had the robo table. You could have a processor at each wheel and a processor for the user interface. And instead of having one processor do many things, you have many processors each do one thing. Then for system architecture, if you break functions in that way, it's modular, so you can add and remove functions separately. You can reconfigure by changing modules. You can collaborate between nodes. Debugging is an important one. If you break up functionality like this, you can debug and test each module separately. And if they break, you can repair them separately. So instead of one big processor, everything revolves around, there are many benefits just in system development to break your system apart like this. And then a final benefit you get from that is one part of the system might have high voltage, one might have high current, one might be measuring very low level signals. And so by breaking the system into modules like this, you can prevent interference. So there's strong reasons to make a network, even if it's only in one box. Or another example is in the machine building we saw, we're moving from central controllers to machines that are networks for all of these benefits. So I'm going to first talk about wires. Then I'll spend a while talking about principles of networking, and then we'll end by talking about radios. So the very first network is, we've been using for multiple purposes variants. Let's see, it looks like analog devices bought Maxim, and so that link is broken. Fix. But what that link is to, when we do serial communication, the simplest version is the host has a transmit and a receive, and you receive the transmit and you transmit to the receive. And so that's two devices talking to each other. But what you can do is this, where you have multiple devices all connected. And so this is called multi-drop. Now, the transmit part is easy. The host transmits and all the devices listen. And they need to know who you're talking to. So the simplest way to do this, and I'll describe many alternatives, is you hard code, like each one gets an identity in its code. And then they can't all talk at the same time. So you need to figure out who talks when. And a simple way to do it is, remember, outputs can be low, high, or tri-state. They can be disconnected as inputs. So the idea is, initially, these are all inputs on the output, which means they're not fighting over it. And so the host sends a message, a node decides it's going to it because it matches its code, and then it takes over the output, it sends its message back, and then it goes back to tri-state again. So that's called multi-drop, and RS-2322485 are standards for that. And here's a really simple example of it. So in this simple example, I'm running a ribbon cable. These IDC, the insulation displacement connectors we use, the wire can go in one side and outside, so it can go to multiple nodes. Then on each node, it's getting, I'm sending in power and ground, and then I'm busing transmit and receive signals. So then in this simple example, I'm typing out the node ID. When I type a character, all the nodes flash. The first flash says they saw traffic. And then after that, only one node will flash. And that's the node I'm talking to. And then it'll send back a message. So you'll see two flashes, one flash, then two, one flash, then two. And then this is the node answering back, but they're taking turns, and only the node I'm talking to is answering back. And so in the code, each node has a hard-coded identity. Then in the software, it reads a character. That's the first flash. Then it asks, does it match my ID? And if it does, it sends out a message. That's with the Tiny 45. And then Adrian did the same thing. Here's a version with the 412. And same sort of code, that the node waits, gets a character. If it matches, then sends a message back. So if you ignore everything else I talk about for the rest of today's class, this is all you need to do to make a bus network of processors. So this needs a host in charge, but that's usually the case. You need to assign addresses to each node and then hang them off this bus. And so this is good up to maybe, say, 10 processors. I wouldn't use it beyond it. But for order 10 processors, this is a really simple, easy way to make a wired network. So that's just a serial bridge. So that's our first network. The next one is SPI, which serial peripheral interface. Historically, if we, let's see, we're going to do this on SPI. There are two pins called MISO and MOSI. Historically, that was master in, slave out, master out, slave in. For a while now, there's been language like masters and slaves we've moved away from it. So you could use the same characters, but call it master and secondary, or you can call it also gets called controller and peripheral. But in this case, one signal goes from the master out, and then the secondary sends a signal back. And then in addition, there's a select line to tell who you're talking to. So there's a standard Arduino library to talk to SPI. SPI is easy to implement in software. If we come down here, this is an example of a software implementation of SPI that you can do on any pin. One use of SPI, for example, is memory chips. It's a common protocol for memory chips. And a really good use of it is memory cards. So this example is a SD card going to a SAMD11 ARM processor. So on the board is the SAMD11 speaks USB. The programmer here is just to load the bootloader. 5 volt comes from USB that we're regulating down to 3 volts. And then on the card, there's the MISO connection, the MOSI connection. This is the secondary select. This is who you're talking to. And then there's a clock pin. And in SPI, so in RS-232, you just simply start toggling bits up and down, and you agree in advance on the duration of the bit. For SPI and for I2C, we're about to talk about, in addition to the data lines, there's a clock line. And so you toggle the clock line to tell it when to read the bits. And so you don't need to guess when the bits are. The clock line tells you when the bit goes by. So with those pins, you can then connect to an SD. And in the first version I'll show you, this is an Arduino library for SD cards. And so in this code, what I'm going to do is I'm going to open a file on the memory card. I'm going to write a message in it. Then I'm going to close the file. Then I'm going to open the card again, and I'm going to read the file and print out what's in the file. So I'm going to write a file, then read a file. And so if we look at the video for that, so I'm just showing, this is using most of the, it's a pretty large library. I'm using most of the space on the D11. In fact, to save space, I'm not using the bootloader. I'm programming it directly. But now I'm going to talk to it. And so this, I wrote the file, and then it's telling me it's reading back the file, and there's the file contents. So that's using the Arduino library, here's a version where I'm doing this on a tiny 44 processor, and I'm implementing, let's see, I'm implementing it completely in software. So FAT, when you have the memory card, you need to format it for how you store it. FAT is an ancient standard, not really even historically a standard, just a format Microsoft used that's widely used. Messy, ancient format, but widely used. Here's a version where in this version, I talked to the card, and then I stored Alice in Wonderland on the card, and I start printing out Alice in Wonderland. And if you want to see the details, in this version, I do everything. So here what I'm doing is I'm doing SPI in software. Then I'm doing all of the steps of, first you have to wake up the card. And so this gets the card talking. Then once the card is talking, you have to read the configuration information from the file directory on it. Then once you've done that, you need to find where the data is stored. And then once you do that, you can read the file. So you're likely not to need to know all of that. You can use the libraries, but this tells you what's going on under the hood. And this lets you do it on almost any processor. And so what these examples then let you do is you can easily get gigabytes for dollars on these memory cards. And so now if you want to, for example, store WAV files for audio is a great use of this. Or another good use of this is it's non-volatile. So you can use this for data logging if you want to store data over months in a project. So memory cards are a great use for SPI. Abhishek is asking about energy efficiency. There's no real difference between SPI and I2C. There's a small difference in the pinout, which I'll show you now. But yeah, the power consumption would be about the same between them, and a small compared to other power consumption in the system. So I2C has a slightly messy manual. It was initially from Philips for inter-processor communication. They defended it as something proprietary. Two-wire interface was a sort of a workaround to the proprietary. Then the Philips relaxed about that because they're not in that business anymore. And so it's now a widely supported open standard. And in I2C, lots of different things speak it. It's more common now, more popular than SPI. Which of those you use generally just depends on what you're talking to. So for I2C, there's 2 lines rather than 3 lines. There's an SDA and an SCL, and you can take, one is for data, one is for clocking, but you can take turns on which direction those lines go. So I2C initially was just between 2 processors on a circuit board, but Quick and Stemma are almost exactly the same thing from different vendors. These are standard connectors to connect I2C to multiple devices. And then let's see. Yeah, Adrian is linking a tiny 412 example of an I2C bus. In SPI, you pick who you're talking to with this secondary select pin. In I2C, there isn't that. In I2C, devices have IDs. And so vendors get particular, put in particular addresses for their I2C device. In some cases, you can change it as part of the configuration. So Wire is the Arduino library to talk to I2C. You can do it, let's see, in this code, in this example, I'm talking, let's see, this is to the magnetometer. This is using it with the Wire library. And then this is an example that I was showing before. This little bit of code from here to here is everything you need to do I2C in software. It's a very easy thing to do bit banging where you toggle the pins. Doing I2C in software isn't a good idea if the processor is busy doing something else. Otherwise, it's convenient because you can do it on any pin and on any processor. So this example I'll show is, here's a processor. I've got I2C connected. You'll see these two resistors. The way in I2C, we've got a line shared between the two sides, and signals can go in either direction. So the way that's handled is you have a pull-up resistor that holds them high, and then either side can pull them down when they want to talk low. So you don't have to worry about fighting over the line. You have pull-ups that hold it up, and then you have pull downs. You can't do this with the built-in. Remember, pins have switchable pull-up resistors inside, but these are large. This is typically something like 75 kilo ohms, whereas these resistors are typically on the order of 1 kilo ohm. If the pull-up is too large, the transition is too slow, and it slows down the data rate. So you add the pull-up resistors. And you don't need those pull-up resistors in multiple locations. You only need them somewhere on the bus. So this node is power ground, and then the two I2C lines. And then the code on this is just a scanner. What it does is it steps over addresses, and it reports when somebody answers. And so what I'm going to do here now is I'm going to plug in, I'm first going to load the code. So this side, this is a tiny 44, so I program it over UPDI on this side. So I'm going to load the code in. Then once it's in, I'm going to start a serial terminal on this side. And then what I'm going to bring in is, right now it's saying nothing's on the bus. This is a, if we go to, this is an LCD module, and on the back of the LCD module is a chip to convert it to I2C. And so when I plug in the LCD, my board immediately finds it, and it says, I've now got an I2C device connected that I can talk to. So very easy to talk to I2C. You can do it in hardware, you can do it in software, and increasingly many of the sensors and actuators we use speak I2C. I2C use is growing very quickly. So there's lots of use cases. If I had a project where I controlled all sides of it, I would just use serial because it's such a trivial protocol. Otherwise, I would pick SPI or I2C based on what I'm talking to, whether I'm talking to an SPI or an I2C device. Let's see, Pablo is linking. Yeah, UART is Universal Asynchronous Receiver Transmitter. I should just mention UART. That's the name of that's the name of what talks to the serial interface. And on the ARM processors, they have more general configurable serial modules. There are what are called SERCOMs, which are modules that can speak any of these protocols. Okay, so that's wired network, SPI, and the killer app for that is memories. And then I2C, we've seen many examples. If we go back, for example, let's see, let's go to in input devices, the accelerometer that does this is an example of an I2C device. Many of the inputs and outputs we've seen are speaking I2C. USB, the processor, the ARM processors were using speak USB. Then there are a number of libraries you can use. So this is microchips library. This is a HID library. What these let you do is give your device a profile. So once you can speak USB, these let your device, so far all we've done with USB is make it speak serial. But you can make your device act like a keyboard and type letters. You can make it act like a mouse. You can make it act like a joystick or a user interface device. It can behave like a MIDI device. And one of the nice things you can do is you can let your device become a host. And so you can plug other things into your device. So those libraries let you take your device, and rather than having a custom application, you can make it act like a range of standard USB peripherals. Ethernet is less common now. If you want to speak Ethernet, the usual way you do it is this is a module. These are $10, $15 that speaks Ethernet and then has a protocol. And I'll talk about the protocol stack to talk to your processor. Then CAN, LIN, Modbus, DMX, those are all networks that are used in cars and industrial systems and lighting. I wouldn't pick them from scratch in your own project, but there's good support if you need to talk to them for something else you're talking to. So those are all wired networks. Now I'm going to step back, and to really understand the radios, we need to talk about networking more generally. And so far, we've just had a bus. There's one wire, and then we're hanging things off of it. The difference between a bus and a network is in a network, there's topology. So right now I'm in my home office. Then I have a home network with multiple things. My home network goes out to my neighborhood network. That goes out to a regional network. That goes out to a backplane on a national network. And then from there, it makes its way to you. And each of these can go in multiple directions. So the big difference between a bus and a network is routes. That we had a trivial ID for I2C or serial of just a small number of numbers. Now I'm here in Cambridge and you might be over here in China. And so we need to give me a unique name and you a unique name. And we need to figure out the path to get from me to China. And so that's the transition from a bus to a network. So first, nomenclature. OSI is a standards body, and the layers were initially meant to be a set of standards that didn't really stick, but the naming is commonly used. So phi is the physical layer. Are we sending light? Is it radio waves? Mac is how you get access, how you take turns, who gets to talk when. Network is identity, how you know what address to talk to. Transport is how you manage the communication. And then on top of that, these are the applications. So these are notes on a class I teach on the physics of information technology. Just the one thing that explains how the physics works. The one thing to know is the bits per second you can send depend on the range of frequencies and also on how strong your signal is compared to the noise. For wired networks, a simple wired network is you have a wire and the signal is low or high, and then you just have a ground wire. That's called single-ended. What's better than single-ended is differential, where if you have two lines and one goes up and one goes down, now if there's interference that comes in, it could move both of these, but we're not measuring the signal, we're measuring the difference in the signal. So differential signaling is more noise immune and lets you send it on a long distance. Power line signaling you can do, it's become less popular. That's where this is, say, an AC power line or a DC power line. This is ground. And what you do is you take your signal and you couple it in capacitively, and then you couple it out. That lets you send high frequency data over power, but it's vulnerable to noise in the power line, which is why it's not that popular. The pull-ups and pull-downs I showed you, that's an example of we share a wire by it gets pulled up and we pull it down. The example of switching from an output to an input is a way to share the wire by connecting and disconnecting. Then at higher frequencies, if you look at a RF PCB, at high frequencies, let's find a nice example. You'll see these fat looking wires on the PCB. Those actually aren't wires. What those are doing is that's what's called transmission lines, where you have a line that looks like that. And then on the bottom of the PCB, underneath it, you have a ground plane. And what's actually happening is you're guiding a wave that follows the line. So the signal doesn't go through the wire, it actually gets guided by it. And so that's in high frequency design. Higher frequencies still, you get rid of that entirely. And so once you're at microwave frequencies in waveguides, you actually make a tube that guides the high frequency signal. And then finally, when you get to optical frequencies, you have a fiber that guides it in the dielectric. So those are wired. For wireless, each country has a body that manages the spectrum. In the US, it's the FCC. Part 15 is the part that has to do with what we want to do, sending radio messages. And what we care about is this part called ISM. So this is frequency, and then this is who owns that part of the frequency. And the military has parts, the government has parts, companies spend a lot of money for parts, but in each band of frequency, there's what are called ISM. It's historically, that's industrial, scientific, medical. These are bands that are open for anybody. And in the modern computer networking era, these have been taken over by sending data. So 802.11 is Wi-Fi. And we'll talk about that when we get to the radios. 802.15 is Zigbee. Bluetooth, these all live in ISM bands. But there are multiple other ISM bands I'll talk about. Then something that gets reinvented over and over is this is sending radio signals. It's very easy to send data optically. And so infrared remotes were an old way to do that. This gets invented every few years. You can blink lights at nanoseconds. And so this is a standard to take the lights around you and modulate them and use them to send data around rooms. And then you can send data with sound. So the speakers and microphones we're using, you can also put audio through them, either that you can hear or at frequencies you can't hear. So those are all just how we're going to carry the signal. Then the next thing we need to decide is how you impress the signal on light or sound. So you'll see these acronyms. PCM is just controlling the amplitude. PPM is you make pulses and control the time. OOK is you turn the signal on and off. FSK is you shift the frequency. PSK is you shift the phase rather than the frequency. QAM is where you make an array of those. And then spread spectrum is where you modulate the signal with what looks like a random signal, and then you decode it. And then as you go through these, as they get more sophisticated, they become more immune to noise, and they let you use more of the capacity. And so modern cell phones now all use spread spectrum for these reasons to modulate. Then the next thing we need to do is we need to figure out who gets to talk when. In the simple wired bus, I had a computer in charge, but on the internet, anybody can talk anytime. So TDMA is you get time slices to talk in. FDMA is you get frequencies. And the internet protocols, so Wi-Fi or Ethernet, use CSMA. And that's like a cocktail party. If nobody's talking, you can talk. If somebody's talking, you pause. And then you don't start talking right away because everybody would interrupt, but you wait a random delay, and then you see if it's free, and then you talk. So it's basically like a cocktail party conversation is how a computer is getting my message to you today. That's how Wi-Fi works. Your cell phone works typically with what's called CDMA, where multiple cell phones can talk at the same time, but they use different codes that let you separate them. So that gets the message through. Then this is a link to back to that class where I talk about once you start sending messages a longer distance at higher data rates, you'll Jason, CDMA and GSM are orthogonal to each other. GSM is a set of standards for telephony. CDMA is much lower level. It's a standard for channel sharing. Almost always, as you push the performance, there are mistakes. And so the way you deal with that is you send more information than your own message. You send redundant information, and that lets you detect and correct errors. So with all of that for background, and you're likely not to need that directly, but these are terms to understand. Now we're ready to start networking. So this is a lovely reference on networking, this book. A strongly recommended book on networking principles. The Internet Engineering Task Force maintains the standards for the internet, and RFCs are called request for comment, and that's how they get written. And it's an amusing thing that request for comment sounds very gentle. The IETF doesn't have power over you. It's just they have authority because it's useful to follow what they suggest. So here's an example RFC. This is a famous one. This is a protocol for controlling coffee pots, which was a joke in an RFC, but this is what RFCs look like. And far and away, the most important one is this one. This is the specification of the Internet Protocol version 4. And this is the key figure. If you make a packet of data that has that structure and you push it out on the internet, it can go anywhere in the world. And the important, well, in a minute, I'll show you what's in it. This format got almost everything right, but they ran out of addresses. Let's see. Hank, what is this? Oh, this is another computer scientist sense of humor. This is IP over avian carriers.
Pigeons is carrier.
Yeah. So the IPv4 protocol, the one mistake it made was the addresses space was too small. They never expected people to use that many addresses. It was just 32 bits. So IPv6, it simplifies everything else, but it has addresses that are large enough to address essentially everything on the surface of the Earth. And so it's taken more than a decade for this to settle, 2 decades. Most computers now support both IPv4 and IPv6, and slowly IPv4 is disappearing as IPv6 takes over. So what the Internet Protocol handles is an address. The computer I'm talking to right now has an address. Now, there are unique addresses anywhere in the Earth. Because of IPv4 versus v6, there are also addresses that are just local. So I have addresses that are local to my house, and then my house has an address that's unique on the internet. And then you can send messages that go to only one person, one address, or you can send messages that go to multiple addresses. So that's IP. DNS is a key thing, and what that does is it manages the connection between names and addresses. So when you go to fabacademy.org, that turns into a number, and DNS is the service that does that. DHCP is how you get addresses if you don't have an address, and NAT is how you handle local versus global addresses. So if we want to take an example, here's me in Cambridge, and I'm going to send a message of, right now my message is going to, let's see, look, I see Nancy is in Shanghai. So I'm going from Cambridge to Shanghai. The IP address of my computer and her computer lets my packets get to her. But then on top of that is UDP and TCP. So UDP is a very simple protocol, and it has ports. So think of IP as like a street address, and UDP as mailboxes. So on my computer, I'm talking to Zoom. I have a web browser running, and I'm running some other services in cloud computers. And so when a message comes to my computer, it needs to know what application gets it. So these applications have different ports. UDP lets me send a packet that has an address and a port and sends it to the internet. That's one packet. What TCP does is often I have not just one packet, but I have a whole stream of packets to send. And this might be because I'm sending a big data file, or it might be I'm doing what I'm doing right now, which is I'm sending my video that's a continuous stream. So TCP, it handles multiple packets. So you can use UDP for one packet quickly, or TCP for many packets, and that sits on top of IP. Then HTTP is browsing a web page, and that sits on top of TCP. So when you open on your computer a web page over HTTP, you're speaking the HTTP protocol that sits on top of the TCP protocol, that sits on top of the IP protocol, and then the IP protocol sits on top of the physical medium you're using. So that's the stack for the internet. Now, you can talk to this directly. Sockets are how you write to the internet directly. So here's an example of, this is a little program, and I'm going to send a message between two computers. And I'm doing that by writing a little JavaScript program that talks directly to the internet. So I can send and receive packets through a socket protocol. Wireshark is a powerful open program that lets you sniff packets and see what your network is doing. And SLIP lets you do the internet over serial. So before I showed the multi-drop serial, now what I'm doing is I'm implementing the internet protocols over a serial bus. So each of these nodes is actually an internet node. Let's see, Mohammed is noting Zoom over UDP. TCP is guaranteed delivery, but has overhead to acknowledge. UDP is much faster. And so you use that for things where you want fast response, but you don't worry if you occasionally can lose a packet. So now we're finally up to radios. So now we're going to get to Bluetooth and Wi-Fi and all of that. So one of the books I recommend you have in your lab is the ARRL handbook, the Radio Leak handbook. In radio is all of this stuff. And let me show you this on, let's pick a single chip radio. Let's see, I think DigiKey moved some pages around. So I'll have to check those links. Let's open this up. So here's what all happens inside a radio. You have a signal that comes in. Then you have another part that's generating the radio wave. So this part is at low frequency. This is the radio wave. You then modulate the radio wave with your data, and then that goes out through a power amplifier that goes to an antenna. Then there's a sensitive amplifier that reads, this is a high level signal. The receiver reads a low level signal. That's at the radio frequency. It then has to demodulate it back to a low frequency signal, chop it up, and give you the data. So those are all the parts of a radio. And then you need to get from your circuit out to the radio wave. And so you need an antenna. And the things you should know are antennas have a range of frequencies they work in that needs tuning. And so in some cases, you just use the design of the antenna itself, but more commonly, there's a very sensitive part of a circuit that does the matching with the antenna. If you do this wrong, your radio wave doesn't go out through the antenna, it bounces back and comes to you. Let's see. And if you do it right, the signal goes out. Thank you, Arnie. Now, actually, so this is a joke about UDP, but the joke about the joke is UDP isn't guaranteed delivery, but the layers below UDP actually generally do guarantee delivery. So it's a misconception that UDP is unreliable. Actually, UDP is usually very reliable. To talk to a radio, you need an antenna, and then you need a matching circuit that goes from the signal on the chip to a signal that goes through the ether. So now, finally, I'm going to talk through lots of different examples of radios. So this first one is there's an ISM band at low frequencies that gets used for RFID. So, sorry, let's go back. This is a module that costs just a few dollars. And what it lets you do is it appears as a serial device. And then once I start talking to it, it then reports data on the RFID card. So you can put data on the card and you can read data from the card. And in fact, if you open these up and look inside, there's very little inside. And so you can scavenge it, and there's the antenna, and then there's the chip it's using. So very easy to read RFID cards. The one thing you need to know, though, is these are not at all secure. These are very insecure. It's very easy to hack them. So it's convenient for reading tags. There are much more secure RFID protocols beyond these simple commodity ones, but that's reading the tag. Then these are really handy. These ISM bands are not the ones that are used for Wi-Fi and Bluetooth. At lower frequencies, they're less crowded, they go better through buildings, and the signal can go longer distances outside, but it's at a lower data rate. So this is a module for an ISM. These are really handy. This is a module now at a higher frequency, but it's not doing Bluetooth or Wi-Fi. All it's doing is, let's see, there are a number of libraries for these that talk to this particular chip. And two of these can talk to each other, and one of these can talk to a few other ones. And you should think about this as just like a wire through the air. So you only use these when you want to connect one or a few nodes. But if you wanted to make like a car with a remote control, or if you had something wearable that you wanted to go to a base station, these at low cost and low power let you just make, in effect, a wired connection, but do it through the air. So that's what I would use when you just want to get a radio signal between two sides. So now we come to Bluetooth. This is a really nice part. This is, let's see, this one is out of stock, but this is a few dollar module, and I'll show you alternatives to it. This speaks Bluetooth. So in this example, what I'm going to do is, this is the Bluetooth module. On this side, normally it would be the processor. Right now, I just have a serial connection, and I'm going to type commands to it. Here's my Bluetooth module, and I'm going to talk to it directly in this example. So in what you're seeing, here's my Bluetooth module. Then once you start using Bluetooth, all of these chip vendors have apps to talk to the Bluetooth. And so I'm using one of the chip vendor Bluetooth scanning apps. So that's what's running on my phone. Then this terminal is connected to this side, and this one is on my computer. So once I turn it on, right now I'm talking through the wire to the Bluetooth. Then on my phone, I'm going to find the Bluetooth module. And Bluetooth can do many different things. They can act like headphones. They can act like heart rate monitors. And one of the simplest profiles is just serial, just sending and receiving data. So I find what the Bluetooth can do. Then I'm going to send a message to it. So on my phone now, I'm sending a message, and then I send that out through the phone, and then it comes from my phone to the Bluetooth and out to my computer. Now what I'm going to do is, this is the upper panel is my desktop computer, and on my desktop computer, I'm going to use, rather than my phone, I'm going to have my desktop computer talk to Bluetooth. It's going to find this little module. I'm going to connect to the module. And now I'm going to send a message from my desktop to the module and back. So that message went from my computer to Bluetooth, out through the cable and back into here. So that's, and all of that's an example of getting from Bluetooth out to a processor and to a phone or a computer. And so that's one Bluetooth module. Oh, that's a weird link. I'll have to double check all of these links, but these are other versions of popular Bluetooth modules. The NRF52 is a very interesting module. This is a radio, but the protocol in the radio you can program in software. So this is a radio that can act like many different radios that's reconfigurable. Let's see, these are, actually, I'll skip this for time. I will mention these modules. So LoRa is a version of Bluetooth designed for longer range communication. Let's see, these are loading slowly. LoRa is designed not for communication within a building, but city scale communication. So this is a good thing to use over, say, like a farm where you want to get data over a longer range communication. This is a module that speaks the an old GSM protocol. These used to be handy to connect things to phone networks. Slowly, this protocol is dying out. It's a less common part of GSM. And finally, we get to the ESP32s. So the ESP32, let's see, this one, the SHAL is a version of the ESP32 in this convenient SHAL form factor. And these speak both Wi-Fi and Bluetooth. So Espressif has a number of versions of the chip and the modules with them that you can get directly from Espressif, and then there's the SHAL version. So in this example, here's the ESP32. They take a lot of power. I have a bigger regulator. And to program them, you need a reset pin and you need a switch that goes between program and run. And then here I'm connected to, again, an outside network where I'm just going to type commands in. Let's see, the Charlotte is asking, the RP2040 doesn't do any of these. The RP2040 just does USB. You could use it to implement USB protocols. But let me get through this, and then I'll talk about the assignment. So in this example, I'm going to load code into the ESP32. I'm going to get it on a network. And then what I'm going to do is it's going to get a web page. So here's a web page that I'm serving. And up here, my ESP32 went out to the internet, got the web page, and reported it out. In this example, I'm going to make it a web server. So I'm going to load code in the ESP32. Then I'm going to get it on my network. Here's its address. I'm going to go to its address. And then this is a web page that came from there. So my browser went to the ESP32 and it served it. This is a UDP example where I'm going to send UDP packets. Oh, nice. Let's see, Ricardo is showing what's inside the SHAL, the Espressif chip underneath the lid. So what I'm going to do now is I'm sending a message between the ESP32 and a computer over USB when I just want to send a packet. Then here I'm going to talk to the Bluetooth mode. So I'm going to load code for Bluetooth in the ESP32. Then I'm going to use my phone Bluetooth scanner to look for it. Then I connect to my device, and now I can type on the computer and it comes out on my phone, and I can type on my phone and it comes out on the computer. So that's sending data in and out of the ESP32. Espressif has its own hacked version of Wi-Fi to do long-range data, backing off on the timing. And then this is the ESP32 with the camera. And so we saw this in Input Device Week. This was an example where I'm loading code in the camera, and now this is video, a web page and video being streamed from over Wi-Fi from the ESP32. So all of that's with ESP32s. And again, for new designs, if you want Wi-Fi or Bluetooth, oops, sorry, let's go back to for either Wi-Fi or Bluetooth for new designs, I would use the SHAOs because they're so convenient for that. Two final things. Software radio is, computers have gotten so fast, they can implement most of a radio just in software. So software radio are where you essentially just have an antenna and a little analog glue, but you implement the radio protocol in software. And OpenWRT is a nice project that takes access points and replaces their software with a Linux distribution that then let you implement complex, RF protocols, make them do whatever you want as radio platforms. So for the assignment, if you do nothing else, just the simple serial wired bus is a great exercise for this week. It lets you connect a few processors. But then depending on your project plans, you could do, oh, sorry, I skipped over one wired one that's important. So NeoPixels that are strips of LEDs, you buy a whole strip of them. They work with this chip, and what that chip is doing is hop count. The way that one works is we have a very long strip of these NeoPixels, and we don't want to give each one a unique address. So the way this one works is you put in a message, and each of these is connected to the next one, and you tell it how many hops to do. And so it just counts hops into the network. And so nodes are linked by just how far in, and they each pass to each other. And that makes it slower to talk to them, but you can do it quickly because the data rate's fairly quick. And that gets rid of the need on a wired network to give them addresses. Okay, and then we covered all of these different types of radios. So I want you to design, build a network. And the key thing is for this week, there have to be addresses on the network. So you have to be able to talk to pass messages between multiple devices. And then the group assignment is just take any two projects this week, but get two projects talking to each other over the network. Oh, sorry, Charlotte. The Pico wireless, the reason I don't want you using the Pico wireless is I want you to design and build. The Pico is just a commercial dev board. I want you, the distinction always is I want you to paste it into your project. I don't want, so the SHAO is right at the border, but the SHAO is embeddable in your project. I don't want you, this is easier just to use a commercial board. I want you to make the board for this week. Oh, I guess, oh, yeah, it's borderline. If you want to paste the Pico, that's okay. That's on the large size, but if you need all the pins of the Pico, that's fine. There's a soft boundary there. It's really just getting practice with designing and making boards, but if you're already embedding the Pico, that's okay. Let's see, Hank, what is this link? Oh yeah, this was making beacons blinking colored lights.
No, it's announcing the IP address of.
Yeah, doing that optically. That's a nice example. And then let's see, Rodrigo, what are you linking?
That's called OSC, and it's a protocol that's called Open Sound Control related to MIDI, and it's very easy to use. And they have a lot of libraries for Python and processing and Arduino that helps you send simple messages based on numbers and small strings of text. And they use addresses, and it's really easy to use. And I was just wondering if you know about it. And
Interesting. I don't know about that, but I'll link to it. I haven't seen that. I mean, I must have seen it, but I'm
It's
not
related to
familiar.
MIDI, but it can use internet and Bluetooth and other, basically any network.
Let's see. Claire is asking, yeah, things like this are fine, but to understand where the boundary is, like for what you showed, Claire, you showed a $20 module. This is 10 of these for $10. These are $1 each. You know, I want you to focus on these embeddable modules you can put into your projects and use your judgment. There's a soft boundary between them. But the goal this week is to get multiple nodes talking with modules you can embed into your projects.
So to clarify, by embed, do you mean like directly integrated into the board, like soldered into the board, or?
Just that it doesn't have to be soldered in. It can be on a header. So like for the for these, it's plugged in with a header. Just the distinction is, I don't want you making a daughter card for somebody else's dev board. I want you making something you plug things into.
Okay.
And again, it's not a rigid boundary. The goal is, I want you to be comfortable making systems with multiple processors using these types of commodity radios. Okay.
Great, thanks.
So that's networking. And then let's see. Oh, there's a question about, I didn't even talk about the ESP8266. And actually, yeah, we're a minute over, but let me mention the ESP. I shouldn't have skipped this. The ESP. Let me take a minute on that, and then we'll stop. The ESP01. This is the predecessor to the ESP32. This is an 8-bit processor. These are really cheap, simple. If all you want is Wi-Fi and nothing else, this is the simplest way to make Wi-Fi. They're limited in the processing you can do with them. It's a very simple processor. So if you want to do anything non-trivial, I would do it with the ESP32. But if you just want Wi-Fi and connected to something else, the ESP01s are a really simple way to get Wi-Fi. But I wouldn't have the ESP01 do much more than just do Wi-Fi. Yeah, the ESP-C3 has both. There's a link here, yeah, to all of the different flavors of the ESP32. Okay, so wired networks, a tour really just for your background of principles of networking, then lots of radios. And so, as usual, Saturday open time. Monday recitation is going to be a tour through education programs. And then next week, we'll pick up building application software on top of the stack of what we've done. Happy networking. See you at the education recitation. Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Oh, ciao, ciao.
Bye.
Grazie.
Thank you. Toodaloo.
Bye bye.